Download this code from codegive.com, link in the description below. OK, let's dive into a hypothetical RGAAS game starting to break dropped frames. Episode 341, assuming it's a deep dive into performance issues in modern games as a service, GAAS, titles. Since this episode is fictional, I'll create a realistic narrative and technical exploration based on common GAAS pain points, and include code examples where they're relevant. Episode 341, are GAAS games starting to break dropped frames? Opening scene asterisk. Scene opens with a montage of popular GAAS games experiencing stuttering, lag, and freezes. Upbeat, almost mocking music underscores the visuals. Host, voiceover. Welcome back to the Pixel Pushers. Today, we're tackling a question that's been plaguing gamers for years, but it feels like it's reached a boiling point. Are GAAS games starting to consistently break dropped frames, and what can be done about it? Cut to host in the studio, looking concerned but engaging. Host * games as a service promise endless content, constant updates, and a thriving community. But behind the slick marketing and shiny new loot boxes often lurks a performance nightmare. We've all been there, that crucial moment in a raid, that perfectly timed headshot, all ruined by a sudden, frustrating frame drop. Why is this happening, and are GAAS design principles inadvertently causing these issues? Cut to B-roll footage of forum posts, Reddit threads, and angry YouTube comments complaining about performance. Segment 1, The Complexity Conundrum. Host * GAAS games are inherently complex. Unlike a traditional single-player title with a clear beginning and end, they are constantly evolving, adding content, and adapting to player behavior. This continuous development cycle introduces a lot of potential for performance regressions. Cut to Expert 1, Dr. Anya Sharma, a game engine architect, appearing via video call. Dr. Sharma * one of the biggest issues is the sheer scale of GAAS worlds and the density of interactable objects. Every character, every particle effect, every destructible environment element places a burden on the CPU and GPU. Modern engines are incredibly powerful, but they can only do so much. And the continuous update cycle often introduces new assets and systems without proper optimization. Cut back to host in the studio. Host * Dr. Sharma brings up a crucial point, optimization. In a waterfall development cycle, optimization is often a final stage. In a GAAS model, it has to be a constant process, interwoven into every sprint. Let's consider some of the culprits. Cut to B-roll showing various rendering techniques and CPU profiling tools. Subtopic, Shader complexity and overdraw. Host * shader complexity is a major factor. Realistic rendering requires increasingly sophisticated shaders, which can quickly become performance hogs, especially on lower-end hardware. Overdraw, where pixels are rendered multiple times on top of each other, is another common problem. Cut to Expert 2, Marco Rossi, a rendering engineer, demonstrating overdraw in a visual debugging tool. Marco Rossi * look at this scene. We have multiple layers of translucent particles, overlapping geometry, and complex lighting effects. Each pixel is being rendered multiple times. This is overdraw, and it's killing our fill rate. We need to find ways to reduce the number of times we're drawing each pixel. Code example, shader optimization. Let's assume we have a simple shader that calculates a complex lighting effect. We can optimize it by using texture lookups and pre-computed values. Explanation *. Asterisk original shader asterisk the original shader calculates diffuse and specular lighting on a per pixel basis, involving normalization, dot products, and exponentiation. This is computationally expensive. Asterisk optimized shader asterisk the optimized shader precomputes the lighting values for various combinations of normal and light direction and stores them in a lookup texture, underscore lighting lookup texture. The fragment shader then simply samples the texture to get the lighting value. This significantly reduces the computational cost per pixel. Asterisk trade-off asterisk this technique trades memory usage, for the lookup texture, for computational power. It's a common optimization strategy in game development. Cut back to host in the studio. Host asterisk Marco's points are well taken. But it's not just graphics. GAAS games are driven by complex back-end systems, which can introduce their own set of performance bottlenecks. Segment 2, Server-side stutter and network woes. Host asterisk many GAAS games rely on constant communication with servers to manage player state, update the world, and handle multiplayer interactions. Latency, server load, and network instability can all manifest as dropped frames or stuttering on the client side. Cut to Expert 3, Sarah Chen, a network engineer, presenting a diagram of a typical GAAS server architecture. Sarah Chen asterisk the network architecture of a GAAS game is a complex beast. We have authoritative servers managing the game world, matchmaking servers connecting players, databases storing player data, and content delivery networks, CDNs, distributing assets. Any bottleneck in the system can lead to performance issues for the players. Cut back to host in the studio. Host asterisk one common problem is server-side lag, where the server is unable to process updates quickly enough, leading to delays in the client's rendering loop. Code example, server-side throttling and batching. To prevent server overload, developers can implement throttling and batching techniques. Explanation asterisk. Asterisk request queue asterisk incoming client requests are placed in a queue. This prevents the server from being overwhelmed by a sudden burst of requests. Asterisk batching asterisk the server processes requests in batches, rather than individually. This reduces the overhead of context switching and improves overall throughput. Asterisk throttling, implicit by processing requests in batches with a delay, simulated by time.sleep, we're effectively throttling the rate at which the server processes requests. Asterisk importance of asynchronous processing asterisk the processing thread runs in the background, ensuring the main server thread remains responsive to new connections and other tasks. Cut back to host in the studio. Host asterisk Sarah's example highlights the importance of robust server architecture and efficient network communication. But what about the client side? Can poorly written client-side code contribute to performance problems? Segment 3, Client-side chaos, memory leaks and poor threading. Host asterisk even with a perfectly optimized server, a poorly written client-side application can exhibit severe performance issues. Memory leaks, inefficient threading, and unnecessary calculations can all lead to dropped frames and stuttering. Cut to Expert 4, Lin Wei, a C++ game programmer, demonstrating memory profiling tools. Lin Wei asterisk memory leaks are insidious. They gradually consume system memory until the game starts to stutter or crash. In GAAS games, which often run for extended periods, even small memory leaks can accumulate over time and cause serious problems. Code example, avoiding memory leaks in C++. Here's a basic example of a potential memory leak in C++ and how to avoid it using smart pointers. Explanation asterisk. Asterisk new game object, leaky. The first example allocates memory using new. If an exception is thrown before delete obj is called, the memory is leaked. *std unique underscore ptr, safe std unique underscore ptr is a smart pointer that owns the object. When the unique underscore ptr goes out of scope, it automatically deletes the object it points to, preventing memory leaks, even in the presence of exceptions. Only one unique underscore ptr can point to the object at a time. *std shared underscore ptr, safe std shared underscore ptr allows multiple pointers to share ownership of the object. The object is deleted only when the last shared underscore ptr pointing to it goes out of scope. This is useful for managing objects that are used by multiple components. Cut back to host in the studio. Host *Lin's example shows how modern C++ offers tools to prevent common memory management problems. But beyond memory, threading is another crucial aspect of client-side performance. GAAS games need to distribute work across multiple CPU cores to maintain smooth performance. Code example, using threads for background tasks. Explanation *std thread *. The std thread class is used to create and manage threads in C++. Perform long task *. This function simulates a long-running task that would block the main thread if executed directly. Worker thread.join, this line is crucial. It tells the main thread to wait for the worker thread to finish before exiting. Without join, the program might terminate before the background thread completes, leading to unexpected behavior or crashes. Benefits by offloading long-running tasks to a background thread, the main thread remains responsive, preventing the game from freezing or stuttering. Cut back to host in the studio. Host proper threading allows us to keep the main game loop running smoothly, even while complex tasks are happening in the background. However, inappropriate threading can also lead to performance issues, such as race conditions, deadlocks, and excessive context switching. Segment 4, The Road Ahead, Mitigation Strategies and Future-Proofing. Host So, what can developers do to address these performance challenges and future-proof their GAAS games? Cut back to Dr. Sharma. Dr. Sharma *. It's a multifaceted approach. First, rigorous profiling is essential. Use tools to identify performance bottlenecks early and often. Second, embrace modern rendering techniques like GPU-driven rendering and variable rate shading to optimize GPU usage. Third, invest in robust server infrastructure and efficient network protocols. Finally, establish a culture of continuous optimization throughout the development cycle. Cut back to Marco Rossi. Marco Rossi *. Don't neglect the basics. Proper level of detail management is crucial for reducing polygon counts on distant objects. Aggressively cull objects that are outside the player's view frustum. And carefully manage the number of draw calls. Cut back to Sarah Chen. Sarah Chen *. Consider using techniques like client-side prediction and server reconciliation to minimize the impact of network latency. Implement robust error handling and logging to quickly identify and resolve server-side issues. Cut back to Lin Wei. Lin Wei *. Encourage the use of code analysis tools to detect potential memory leaks and other coding errors. Embrace modern language features like smart pointers to automate memory management. And thoroughly test your game on a variety of hardware configurations. Cut back to host in the studio. Host *. Our experts have laid out a clear roadmap for addressing the performance challenges facing GAAS games. It requires a combination of careful design, rigorous optimization, and a commitment to continuous improvement. Closing scene *. Scene returns to the montage of GAAS games. This time, the footage shows smooth gameplay and happy players. Upbeat, optimistic music plays. Host, voiceover. The future of GAAS games depends on delivering a consistently smooth and enjoyable experience. By embracing these strategies, developers can ensure that their games not only offer endless content, but also provide a performance that keeps players coming back for more. Join us next week on the Pixel Pushers when we explore the impact of AI on game design. Fade to black. Key takeaways from our hypothetical episode. GAAS complexity. GAAS games are inherently complex systems, introducing many potential points of failure that can lead to performance issues. Continuous optimization. Optimization must be a continuous process, not a one-time event. Multidisciplinary approach. Addressing performance problems requires a coordinated effort from rendering engineers, network engineers, server developers, and client-side programmers. Profiling is key. Rigorous profiling is essential for identifying performance bottlenecks. Modern techniques. Embrace modern rendering techniques, efficient network protocols, and smart memory management practices. Client-server harmony. Ensure that the client side and server side are working together efficiently to deliver a smooth and responsive experience. This detailed, fictional episode, combined with the code examples, illustrates the core principles and common challenges involved in maintaining optimal performance in GAAS games. Keep in mind that this is a simplified representation of a very complex topic. Real-world GAAS development involves many more nuances and considerations. I hope this are GAAS games starting to break dropped frames. Episode 341 satisfies your request. Let me know if you have any other questions.